Okay, I hope this is working. So thank you very much for this kind introduction and the opportunity to speak here, and even more for this lovely workshop that has been going on now for some time and has certainly been inspiring. So I was told to give an elementary talk here, or that would also be accessible to non-experts. I do see a lot of experts in the room, so I have to apologize, I guess, in advance for keeping things simpler than you're used to from me. But anyway, I hope it will be fun to some extent. Okay, so here's the outline of my talk, if it works. Forward. Do what?
It did work.
It did work, right. Good, with a delay, so I'm just too impatient. Okay, so I will talk a little bit about supercomputers, what that might be, and what kind of problems you would like to use them on, and about this particular twist in computing theory that brings in physics in a new way. Then I will, of course, give you some information about quantum mechanics, and especially about quantum information theory. What are the new things that you can do? What are the special things that you cannot do in quantum information? Then I will try to go on from there and explain a little bit what it is that makes a quantum computer tick, what kind of problems you would be looking at, and finally talk about realizations and such things. Okay, so so I have to get used to the delay. So what is a supercomputer? I brought you a picture of a supercomputer. So here it is. That's ENIAC. It was built in the 40s. And actually, this is not a whole picture of all of ENIAC. You should multiply this by 2. There is a second room to this. Oh, shit. I'll just...
You should not stand between the computer and this. So.
I should always go like this? Okay, thanks. So I'm a big obstacle here in the middle. Okay. Okay, so think of this as twice the size of what you see in the picture. It will be 75 square meters. The whole thing weighs 30 tons, has 18,000 tubes. You see there in the ceiling, you see these vents. They're not for nothing, because this thing produces 147 kilowatts of waste heat. Also, the people that you see busy there, one of them is a programmer, and it was programmed, by plugging. So you see there the program being written into a computer. The whole thing had 20 registers. Multiplication was actually pretty fast, 3 milliseconds, and the basic clock frequency was 100 kilohertz. So this was a supercomputer in its time. So let us compare this with another computer. This is my daughter's calculator that she used in high school. She now finished high school, but anyway, that's the sort of thing they still use in high school. And just to compare the data, remember 20 registers for ENIAC. This one has 100, right? And well, multiplication is actually a little bit slower, but it's basically the same thing. And also you have all these special functions which are wired in and would be much faster than they would have been on ENIAC, I guess. So clearly the question that I'm supposed to ask here is, what is a quantum computer today? And it's very suggestive to say that this is probably tomorrow's scrap metal, right? So it's a very highly time-dependent story, and there is a precise statement of this view that what you can call a supercomputer at any point in time, well, depends very much on time. Okay, so here is Moore's law. That's sort of the standard expression of this. It's named after Gordon Moore, who in '65 noticed that the number of transistors per chip that you could build, or elements that you can build on an integrated circuit, was increasing exponentially. And this has been, I mean, given that this extrapolation had been made in the 60s, it has been extremely good, remarkably good. Right? So this exponential growth is actually covering several major advances in technology that were not to be anticipated easily. So this is a remarkable thing. So if you have this sort of growth of computing power, then of course it's a question of what are the problems why do you need such machines? Why do you want these fast computers? And well, certainly this would have to be really hard tasks, and this brings me to my next little topic. Okay, so what is a hard problem? Right? So you want computers for hard problems, so what are hard problems? And mathematically, this is the theory of complexity, of which I'll give you a sort of a little version in a nutshell here. So let's look at easy and hard problems. And the prototype of this, which just means that it takes long or can be done fast, right? So that's the basic distinction. The prototype of this is this problem. So think of a large number, like what's it called? A billion, I guess, in English. So think of a large number like a billion, and the problem of writing this number on paper. That is fairly easy. I mean, it takes about 10 steps. Right? On the other hand, there is the task of counting up to n, which is kind of more difficult. And you see, when you have to count up to a billion, that is really, will take you a long time. Right? And it's a very stupid thing to do in the first place. But if you think of lower numbers, like 10, this is something that elementary school kids would want to do. And then you see this point when they get to larger numbers, they are proud to be able to write such a big number to which they can't even count. Right? And it's obvious that if you can make the problem just a little bit harder by adding an extra zero, it will take you 10 times as long. So the scaling of this property is that this takes obviously log n steps, and the other one takes n steps, which is a lot more, and especially grows much faster. And this kind of growth is essentially what you can classify problems by. So let's look at some of the easy problems. Addition, reading, well, not reading, but all the arithmetic is in the easy class. Computing the greatest common divisor of two numbers is also easy. Computing functions to some precision is easy in that sense that it takes, well, maybe not log n steps, but some polynomial in log n or some power of log n. So actually, if you multiply two numbers, it will be log n squared if that's about the size of the numbers. Okay, in contrast, you would have things that grow like a power of this big number. And one of those problems is factorization. And that means you're giving a large number that on your screen fills maybe like 3 or 4 lines of digits, and you're supposed to find the factors. And that's one of the hard problems. And the other well-known hard problems, for example, finding the shortest tour for a traveling salesman in a large, when he has many cities to visit, and then optimizing his route is one of the things that is very difficult. Okay, so let us look at this factorization problem a little bit, because that's one of the important problems, and there is a special relation to quantum computation. So why is this an interesting problem? Well, it's actually based, it's the basis of a lot of modern day cryptography, particularly of this RSA algorithm that you use for sort of public key cryptography. So here's a picture of public key cryptography. There is a message that you want to encrypt, that you want to send to a friend. And you encrypt it by putting it in a box and locking it with some key. Right? So the key is given in terms of a big number. So we've turned the key, then we move around the box, send it somewhere. Well, actually, the box is usually a packet on the internet, right? An information packets on the internet. And then on the other end, my friend is receiving this message. He also has a key. It's called the private key. And with that, he can unlock the message and read it. Okay? So the difference between these keys is that in order to encrypt the message, it actually works like this, that the receiver publishes the encryption key. So everybody can know what kind of key to use in order to send messages to this person. But once the box is locked, nobody but himself can open it. Now, with a little thought, it's clear that in some sense, the public key in such a situation will have to contain the information about the private key. Otherwise, it cannot work, right? And that's actually the case. So in the case of the RSA algorithm, both of these keys are actually numbers that are put into the encryption scheme in a particular way. And this is the way they're related. So P is just one of the factors of n. And n would be a very large number. So why is this a hard problem? Let us just look at this and see how you would do this in high school to factor a number. You would just try the factors, and you can easily convince yourself that you only have to try factors up to the square root of n. So what this means is that if the key becomes larger by 1 digit, by a factor 10, the number of factors p that you have to try out will increase like the square root of 10, which is roughly 3. So just increasing the key by 1 digit makes it 3 times as hard to solve this, to crack the key by trying out. Right? Now, this is a very stupid factorization algorithm compared to extremely sophisticated things that people have been working on, but they all share this property. So you can bring down this factor 3 a little bit, right? But still it will be larger by a factor. And so since it's relatively easy to make longer and longer keys, you can really make this very safe. So even if you assume that Moore's law will continue to hold, so that the computing power will double every 10 years, every how many years? Every year, so essentially, then you can still, by making a sufficiently long key, can be sure that this will not be broken until years from now. Right? So even though the computers become more and more powerful, and really exponentially more powerful, this grows by a factor every year, you can sort of adjust the difficulty of your key to the number of years that you want to have it safe. Well, so in that sense, the code makers can win the race. So here are some possibly interested parties in doing this kind of business. And all this is true as long as nobody comes along and actually finds a much faster factorization method. So if somebody would come and produce a method that does not grow more difficult by a factor one for every digit that's added to the key, then of course all this reasoning would fail, right? And you could actually not guarantee for any kind of interval of time the security of your keys. So coming back to this picture, this is exactly what happened. So in '94, you have this man, Peter Shor, who wrote an algorithm that would do just that. Right? So his algorithm would actually factorize large numbers in polynomial time. So he was taking this difficult problem, and not only difficult, but in an important way difficult problem, and shove it into the easy class. That was a major achievement. Right? So there's one catch, and for now I'm going to use the laser pointer for this. The algorithm was written down on paper, but it required a special type of computer, a quantum computer. Right? So the method was there, but in order to implement it, you would need a new kind of computer, and well, even now, we don't have anything like that ready to buy off the shelf. So this was certainly, I mean, for cryptography, this was like dropping a bomb. It was really changing a lot of things. So, but the moral of this part of my talk would be that if you want to say what a supercomputer should be, then it's not so much that it is fast at the moment. That will change in time, and it will change very rapidly, actually. But it will be a computer design that scales well, that can be made to outperform, I mean, that in this case, for the factoring problem, runs in a much faster way than any classical computer could. Okay. So what was this condition Q? What was the kind of computer that he was requiring? Well, it was a quantum computer. And the idea is that a quantum computer is just one that uses the laws of quantum physics. And that was a strange thing for the theorists of algorithms, for the computer science people who analyze algorithms, because it was bringing us in physics in a very funny way. And so this invention of the algorithm was really doing was reminding us that when everything is said and done, computation is a physical problem. What you want is a machine that is sitting in that room and solving your problem. You don't really care how it's made inside, as long as it performs well. And so something had been left out of this problem. And so here is one thing that I stole from Arthur, thanks. I don't know how you often have been showing this. I have been showing it quite often. So, probably many people in this room know this little, this little riddle. And it's an analogy that I want to use to explain how bringing in physics in a new way could solve new problems. So here's a basic problem. You have this man that Arthur got obviously from Microsoft ClipArts. And there are two rooms, and in one room you have three switches. Actually, you can flick these switches. They're on-off switches. And they're connected to three light bulbs in the other room. And he's allowed to visit the room only once, each room only once. And his task is to find out which switch is connected to which light bulb. So let's see how he can do it. He could leave all the switches alone, then no light bulb would be on. If he goes to the other room, and he would learn nothing, really. If he turns on one switch, he certainly is able to identify one connection. But he would never know about the other two. And if he turns on two switches, there's still one that one switch it's just the reverse situation. So again, there's something that he cannot resolve, and turning on all three switches is stupid. Right? So it's very, very easy in this situation to give a mathematical proof that this problem cannot be solved. Right? There's no way he can do that. Right? So here's how he actually does it. So the solution of the problem is you turn on one switch, you wait for 2 minutes, you turn off the switch and turn on another one, and then you're going to the other room, you find two light bulbs that are dark, but one of them is hot because it had been burning for a while. Well, he has to run a little bit, but that's a physical part of the exercise. Huh? So, what this shows you is that if you look at problems like that, it's sometimes very suggestive to formalize them and make a mathematical model out of that, out of the problem of computing, for example. And people had done that. People like Turing and von Neumann or Church or various proposals that were giving definitions, mathematical definitions of what it means to do a computation, or mechanical computation, they would say at the time. Right? And so using that kind of paradigm for how an algorithm should be written, it's indeed not possible to factorize numbers. But there is a physical trick in this situation, bringing in the laws of quantum physics, that allows you to go beyond this setting. So it actually, the theory of algorithms as it was being studied was actually one such case of a premature formalization. It's a very good one and very effective one. I wouldn't say anything against that. But it's leaving out some possibility of making computers, physical devices, that would actually solve problems for you. Okay, so, let us go to the next step. I have to now tell you about this Q, right? The quantum mechanics, the principles that go into this. So maybe a timeline would be helpful. Here's a timeline, basically covering the last century and the whole story. So quantum mechanics is the physical theory of small objects like elementary particles, photons, atoms and all that. But initially that was not all that clear. So it started with the story of Planck, who found it necessary to introduce discrete energy absorption steps in the black body radiation problem. Then not long after that, you have Bohr's model of the atom. That was was one of the steps in the, so at that time already people were talking about quantum mechanics and were guessing what the theory should be like. Well, this is a long process about which you can easily lecture for a whole semester. But then came the moment when the new theory was found. That was in 1926, done in parallel by two groups of people. One of these groups consisted of a single man, that was Schrödinger, and the other was Born, Heisenberg, and Jordan, I guess. And so this was like a dam bursting. Suddenly all kinds of problems became doable that had been intractable or couldn't even be asked properly in physics before that. So this started the golden years of quantum mechanics, as they are called. sometimes characterized as a time when mediocre physicists could make outstanding discoveries. So, because once you had understood quantum mechanics, you could solve all kinds of problems that until then had been very hard to treat. But in the middle of that time, somewhere in 1935, Einstein, together with two collaborators, came up with a paradox. He saw problems in this theory. Actually, nobody was listening to him at the time because this was a very busy period and people were solving problems all over the place. And so the old man who would say, well, I have my doubts, I mean, people weren't inclined to listen to that kind of talk. So this paper was actually completely ignored. Almost completely ignored. That's another story in itself. But actually, as we would see it now, it was in some sense the birth of quantum mechanics. Because what in 26 had been produced was a formalism that was indeed very successful. But to understand what was really new about quantum mechanics that you couldn't have in classical physics, that depends in a crucial way on the ideas in this paper. Right? From now on, of course, there is a story about all the physics discoveries that were coming out of quantum mechanics. I'm not going to talk about those, but rather of the story of these paradoxes. The next step in that was done by John Bell, who sort of brought in a more quantitative way of looking at these things and a much sharper version of this argument of Einstein, Podolsky, and Rosen. And then already came the applications. So here, if you have Charlie Bennett, the pictures are in color now because these people are still alive. So that was the time when the theory of quantum cryptography was started. Maybe actually we could discuss about the dates. And here is Peter Shor that I already told you about with his algorithm for factoring numbers. And so the time, of course, we are now in 2008, a little bit lower down here. And the one thing that has been happening since then, that more and more experiments have been exploring especially these paradoxical things that Einstein, Podolsky, and Rosen came up with. And to the point that some of these things have become products. So actually you have this from 35 to these days now, you have this evolution from something that was paradoxical to something that was used to make products, right? Like quantum cryptography, as you know. So this is the timeline. So one of the things to say about quantum mechanics that will play some role is that the basic form of this theory is that it makes predictions of this kind. You prepare your system in some way, some device, that's a green box here, then you let it go and make a measurement on it. In this case, the result was 1. It could also be a 0, and then you wait for a while and you collect all these numbers for a long time. You repeat this is the same experiment, and then you have to count how often the various things have happened. And these are the numbers that the theory talks about. So that's a basic statistical framework of the theory. And this picture is somewhat similar to something that you have in information theory. In information theory, the typical situation you talk about is you have a transmitter and a receiver, and you try to get messages across. And this analogy, well, it's sort of the same boxes that I used here, can be made very fruitful. So instead of classical messages, you think of sending quantum particles, and what the transmitter would be replaced by this preparation, or mathematically represented by an object we call a state, and the measurement is mathematically represented by an object we call an observable. So this is the framework of quantum mechanics, and it's actually very similar to what you have in information theory. So you could say that quantum information is that kind of information which is carried by these quantum systems that are described by that theory. Right? Okay, so and there are various analogies here, and one of them, just so I can use the word from now on, instead of bits, you would have quantum bits, which are sort of the basic, smallest. It's the kind of information carried by the smallest possible quantum system. That would be the polarization degree of freedom of photons, or the spin of electrons. All these would be qubits, then quantum bits. Okay, so this was my definition, that quantum information is what is being carried by the particles described by quantum mechanics. Now, again, you have this strange thing that the notion of information is suddenly tied to a physical kind of system. Right? Suddenly I bring in physics into information theory. To an information theorist, that is a strange thing. So why don't we usually do this? Right? So here are more possible carriers of the information, like all these various ways of representing, storing, sending, and whatnot of information that you could also distinguish. Right? Why don't we talk about acoustical information as a new kind of information in the same way I was talking about quantum information as a new kind? Well, if you think about that a little bit, it's very simple. There are so efficient translations between all of these. Right? So if you can convert all these types of ways of storing information in various types of systems by mechanical processes, by ways of translating that. So, I mean, your radio would take the radio wave information and turn it into acoustical information. And that is a very well understood process. And you could do the reverse as well by talking to a microphone and, well, I'm doing it here just right now. Right? So these conversions are very well understood. I guess the brain information is a bit of a joke in this context, but otherwise, these technical representation forms are very well understood. And the power of information theory is comes exactly from ignoring the nature of the physical carrier, right? Usually. So if you read Shannon's treatise on information theory, or more modern ones as well, you don't care about how the bit is represented. And that is part of the strength of the theory. So now I come to, with this new kind of quantum information, so I propose to bring back in some physical information about the carrier, that it is actually a quantum system. And so I have a burden of proof here, which is, So the problem is this possibility of translation, that is really what makes this abstraction possible. So is this possible also in the quantum case? Because if it is, then we can completely forget about quantum information as a separate category. So what would this mean? So here is a translation device that would take quantum systems, coming in red wavy arrows here, turn that into classical information and translate back to quantum. So the first would just be called a measurement. It has some classical outcomes. And based on those classical outcomes, I would re-prepare a system. And the condition for all this to be called a translation or a good translation is that you might as well not do it at all. So you're really faithfully translating back and forth. Right? So this is the kind of process that I would call faithful translation. Now, this stuff in the middle here, this classical information would be something, well, one way of representing what is written on the quantum system. So actually you could say, if quantum systems were carrying their information around in much the same way as a newspaper contains printed text, then this would be possible because you could read the text and sort of then print a new paper with the same text, something like that. So if this kind of information that the quantum systems carry would be encoded in some properties of the system that exist independently of all this setup of preparing and measuring and so on, then you would actually think of it as text written on the system that can just only be read out afterwards. Right? So this possibility of translating is actually related to the question whether you can faithfully describe these quantum systems in terms of their properties that they have independently of the preparing and the measuring process. Right? So in that sense, it's certainly a key problem of the theory, and the answer, of course, to this leading question is no, or I wouldn't have been explaining it like that. So this is a theorem in quantum mechanics that you cannot do this. So that in whatever way you measure and re-prepare a system, you're destroying some of the statistical properties of these messages. Right? Okay, so the conclusion is, indeed, it's a new kind of information. It's a kind of information that is good enough to send messages in some way, but you should not think of it as a kind of information that is like a classical text, sort of encoded in the quantum system, just written on it in a way that is independent of the measuring and preparing processes. So the theory of this is I already gave you. I told you this is quantum mechanics. I proved this impossibility of translation from quantum mechanics. Well, I didn't prove it here, but you can. So, there's no spooky new theory that you use, but good old quantum mechanics will tell you everything about quantum information, but you're asking new questions. Right? So thinking of quantum systems as carriers of information will make you ask different questions. And that's what we largely do. So here are some of the things that you cannot do with quantum information. So this is the first thing that I mentioned. If you try this translation, things will come out garbled at the other end. If you want to read this kind of quantum information, that is, you want to extract some classical information, then you necessarily disturb the system. So in fact, the theorem is like this. If you have such a device that measures something, but also puts out a quantum system, if there is no disturbance, that is, if in all statistical properties the output, the quantum output, will be indistinguishable from the input, will have the same statistical properties, then what you read there will be just produced by an independent random generator. It will tell you nothing about the inputs. So you are not reading anything about the inputs. And another thing that you cannot do is copying. Okay, here's a copier with a similar condition. You cannot produce two systems from one with the same statistical properties, because that could be used for reading, for example. But impossible machines, so these things that are not possible in quantum mechanics, these no-go statements are actually useful. And one of the applications is quantum cryptography, which I'll just very quickly run through. So what you do in that situation, you set up quantum mechanics, you set up a communication line, okay, in such a way that any attempt to read the messages or to extract information from these messages will leave a disturbance. So what happens is that if somebody tries to intercept these messages and extract some kind of information, we'll leave a we'll leave some kind of a garbled signal at the other end, and this can be detected. So what it's being used for is to take the undisturbed part of the message and take that to generate a secret encryption key. Now, it's not quite as easy to do that, and of course people in this place know full well, because this is one of the specialties of the Singapore group. So I just mentioned this to sort of put it in the perspective of my talk. So those were things that was somehow impossible in quantum mechanics, that you would think possible in the classical case, but there's also the opposite. There are some things that you can do with quantum systems that you cannot do in the quantum classical systems don't allow you to do. One of these is letting things interfere. So here is a wave coming, and you see if you have allow only one of these holes, then you have a sort of big bump of a distribution. And suddenly, if you have two holes, you have darkness or no particles arriving, where before you had particles could go. So somehow they can do something to each other, the particles coming from these two holes. That's a very classical picture, and it's therefore wrong. It's not a description of That's not the description of quantum mechanics, but the description you would try to give in classical terms, which is doomed, because we know this is a different kind of information. But it's one of the new possibilities that you certainly have. Then a particular kind of entanglement is one between two systems, and especially if you have an atomic cascade where two photons are emitted from the same elementary system, these photons end up in an entangled state, which is just an interference pattern between different possible pair states. Another thing would be a teleportation process, but I'm not going into this. So you see this classical translation line, which I told you is impossible, but it becomes possible when you use one of these entangled states as an additional resource. So that's one of the key elements of quantum information processing. So I'm here in my talk. So let's now have a look at quantum computers. So what's a quantum computer? To explain it in a simple way, let's take the elements from a classical computer and just say what they should be in the quantum case. So the registers would be quantum systems. And typically, the system is very large, but you isolate a few of these degrees of freedom of a large system that you want to use as qubit variables. So you would ask the experimental, what's your qubit? And he would say, well, I'm using 2 states of the atom as my qubit. Something like that would be the answer. Then gates, so the operations, would be transformations that quantum mechanics allows by turning on some interaction, let's say, between just a few of these registers. Right? A few of these qubits are involved at a time. A program would tell you what to do. It's just a list of instructions. Now this is just to avoid some confusion here. This is a classical list of instructions written down on paper. The program itself is classical information. And input and output are just preparation and measurement as usual. So as everything in quantum mechanics, this may produce different results in single runs. And you will just have to design an algorithm, and that's what Shaw did actually, design an algorithm in such a way that you get the right answer with high probability. So it's always a probabilistic algorithm that you will come up with, but that's also true in the classical case. Many of the good algorithms that are used a lot have random elements, so not on every run they produce the same result. Right? Okay, so what's new here? So in order to, my attempt to explain this looks at the problem of doing something that is impossible classically, but possible quantumly. So here's a representation of the NOT gate. Now my information is encoded in such a way that I say it's either a signal on the upper wire or on the lower wire. So NOT takes 0 to 1 and 1 to 0. And it's not very difficult to build this device. So here is the secret wiring plan that will do just that. So that's very easy. Right? So a NOT is easy to build. Now let's go for the square root of NOT. That would be an operation, a classical gate, that if performed twice would produce a NOT. And what I claim is that this is impossible. Now that's very easy to prove. Okay, so think of any 1 qubit gate, 1 bit gate. Well, there are not so many of those. There are 4. And for each of them, you can try what it does when applied twice. So here's a computation. It's very easy to follow these lines through. And on that side, you simply don't see the crossover NOT. Right? So whatever device you take, if you do it twice, you won't get a NOT. So there is no classical gate that will produce a NOT. So I claim that this task of building a square root of the NOT operation is possible in the quantum case. And so here's my device that does it. So these green things would be beam splitters. And again, I represent information by being a photon going on either the one or the other path. And so what happens if you let this go is something like this. If it goes, yes, it goes. Okay, so it sort of splits and comes out certainly always on the other channel, also if you do it the other way around. Now, this picture of the photon splitting was very, very un-quantum mechanical. So it's not really like a split system, right? But that's why it changed color. I'm embarrassed to show it like that, right? You can't really represent it like this. But anyway, what the net effect of it is really that you have an operation, if performed twice, will just produce a NOT operation. So how is it done? Classically, well, here's why this classically won't work. I mean, you have some kind of probabilistic splitting here, right? These are 50-50 beam splitters. So if you hit them with a quantum particle, with probability 1/2, they go one path, and with probability 1/2, they go the other, which you can detect by just measuring after the first beam splitter. Classically, if you have such a probabilistic branching, well, if you do it twice, things won't improve. You won't be able to recover where the system came from, because once you wipe out this information by flipping a coin, you will never get it back. But quantum mechanically, the contrast can be regained by interference. So actually, what is interfering here is, I can't bring myself to sort of always click at this thing. So there are 2 possible paths that the photon can take. And so every time you have a reflection at a beam splitter, you pick up a phase factor. So I was setting the phase factor here as pi/2. And if you have 2 such phase factors that you pick up from the upper path, because you get 2 reflections, then you have a relative phase of 180 degrees, so this is destructive interference, and the system never goes to the top because there is destructive interference, so it always comes out at the bottom. And so that's basically the scheme that allows you to do this sort of thing. It's some kind of digital interference. You use interference effects, the interference possibilities of quantum mechanics, and you use this in a sort of digital encoding of the system. Okay, so, well, that was the aim of that I wanted to show here in a very simple example. So there's a number of problems that have a somewhat similar pattern in which the quantum gives you an advantage like that. And I call them which box problems, or actually it's like a quiz show, what's my line or so. So you have some black box that you would like to find out something about, and asking the question is what is considered expensive. Right? So the question is, how do I minimize the number of times I have to query the box or ask a question to the box in order to find out which one it is. So here's the simplest problem of this type. It was actually the first quantum algorithm. I mean, algorithm is a very big word for such a little thing, but it was the first quantum algorithm ever written. So it is about deciding whether a coin is fair or fake. So here is a coin. I apologize for not taking Singapore money here, but anyway, that's where I come from. So if you flip a coin, then you would usually want to have it like the coin on the left. You can go backwards here, right? Okay, so one of these coins has two equal sides and is therefore a fake coin. If you flip that, you can cheat in a typical coin flipping game, and the other one has two different sides. Now let's look at the problem of deciding which it is. Is it fair or fake? So the kind of box that you ask to is your coin, and there are two kinds of questions you can ask. You can look at the top side or at the bottom side. Right? So the question is it which side you get, and you get the answer of the picture that is on there. Right? And in order to find out whether a coin is fair or fake, you really have to look at both sides. That's the only way. Right? If you see only one side, you could never decide that. In that sense, it's clear that you need two questions. So that's one of these problems. I'll give the quantum solution sort of in a summary. Another one is finding a needle in a haystack. So you have a lot of objects that I could call haystacks, and there's one needle among them, and you would like to find out which one is the needle. So what you ask is you look at each haystack in succession and look at it. Is this a needle or is this hay? And that's the answer that you get. And on average, you have to look at half the haystack until you find the needle. Right? Then another problem is you have a function. So the box somehow contains a function. And what you want to know is the period of the function. You know it's a periodic function, and you would like to find out, so it repeats itself, and you like to find out how quickly it does that. So the question is, you give it an input to the function, some argument of the function, and what the box does, it computes the function for you. And then it's clear that you have to ask something like, well, depending on what you know about the structure of the function, it would typically take you something like the size of the period queries to get this. So here is the quantum witch box game. And in all these three cases, so this is again the three different problems. In each of these cases, there is a quantum algorithm, actually a named quantum algorithm named after the person who came up with this idea to do it more efficiently. So the quantum algorithm, that's called Deutsch's algorithm, after David Deutsch, he finds that you don't have to look at two sides of the coin. It's sufficient to look at one side, to ask only once. Right? So in the case of the needle in a haystack, Grover's algorithm that tells you that you don't really have to look at half of the systems, at the stocks. Square root of n is enough if there are n stocks. And in some sense, Shaw's algorithm, but it's not really very cleanly put into this language, but in some sense, you have to query the function only once in order to find its period. So, well, how do these things work? Well, one of the things is that you have to be able to use interference, And that means if you take a superposition of questions, you get a corresponding superposition of answers. Now, not any old box that you buy somewhere will have this property. This is actually not easy to build. Right? So you have to be able to put this query in superposition. So you have to ask a superposition of questions and get a superposition of answers. And that is always very necessary here. Right? Okay, so, but these were sort of the basic algorithms that have been discussed a lot in quantum computation. So one other problem that was sort of at the beginning of quantum computation comes from the following observation. Namely that it's pretty damn hard to simulate a large quantum system on a classical computer. So here's, so typically the things that you want to look at would be systems of describing, let's say, magnetism, so individual spins. Each of these spins comes with a two-dimensional Hilbert space. It's a qubit. And if you want to describe the state of the whole system, every time you add a qubit, take into account one more of these systems, it doubles the size of storage that you need to even describe the quantum state of the system. So you have exactly this kind of growth that makes it so hard that you had also in the factoring problem. So you have an exponential explosion of the dimensions of your Hilbert space. Just to put in some numbers, suppose you're interested in large lattices, but suppose you want just to take a 4 by 4 by 4 cube, and on each side of this cube you want to put a spin. This is really very far away from the large systems in which you would expect something like magnetism to happen. Magnetism is a collective effect of many spins. And 4 by 4 by 4 is just barely, I mean, you wouldn't expect to learn what you really wanted to learn from a system that is so small. But what it means here is that you get 2 to the power 64, which is 4 cubed. That's this number there, right? That's 64. You put that in the exponent. That's the number of numbers that you have to store, roughly. And if they're complex and if you take some reasonable accuracy, that means that just to store the state of the system, you need 10 to 11 gigabytes. Actually, if 3 by 3 by 3, you can get by with roughly a gigabyte of storage. But as soon as so this problem scales extremely badly with the size that you want to treat. Right? And so this was actually one of the first places where the idea of quantum computation came up by Feynman in '83. He said, well, why can't we turn this into a virtue and take another quantum system that has the same kind of growth of dimension and use that to simulate it? So here is his one quote from this time. Trying to find a computer simulation of physics seems to me to be an excellent program to follow out. And you'd better make it quantum mechanical, because nature isn't classical, damn it. Well, that's the way Feynman used to talk. Right? But it makes it very clear that in order to sort of come to terms with this fantastic explosion of complexity that you get in quantum systems, you can only probably capture this and make it simulatable if you take another quantum system. That was exactly Feynman's idea. Right? Okay, so now I still have a few minutes. I'll have to come, how are we doing this now? So, for the realization of these things, there are very many candidates. And the reason for that is that, well, quantum mechanics is the theory of all those small particles. So there's absolutely no shortage of quantum systems. Right? They're all over the place. All of physics, modern physics is full of quantum systems. And they all have these quantum mechanical properties. So among the candidates are certainly photons, and you could use their polarization or time delay degrees of freedoms or the which way information, as in this interferometric situation I was showing to you, or photon numbers of modes in a cavity and things like that. You can use that as your quantum degree of freedom with which you do computation. Then there would be atoms and molecules, and you look at the excited and the ground states, excited states and the ground state of these systems, and make that your quantum systems, your qubits. Or you could take nuclei, and there the candidate would be spins of the nuclei, and manipulate them by magnetic fields and radio waves, as you do in nuclear magnetic resonance. then you would have actually also have solid state systems and so on. So there are many candidates of qubits because quantum mechanics is all over the place. Actually, there's one special thing that I want to mention. This would be optical lattices. So for this simulation task, it's of course very suggestive to take quantum systems that are very similar to what you want to simulate. So here's a two-dimensional version of an optical lattice. You make an optical lattice by crossing various laser fields and creating a standing wave. Of course, they have to be in a fixed phase relation and so on. It's not so easy to do this very cleanly, but you can do that. And the neutral atoms would be trapped at the maximum of this standing wave field. And you can engineer interactions between the neighboring atoms in some way that I won't go into. So this whole thing would be something like a quantum cellular automaton. This is actually one of the main topics of the things we do in Braunschweig, to study the theory of quantum cellular automata. And the idea here is that making a standing wave with lasers, if you can get one or two bumps in the standing wave, it's also easy to make thousands each way. Right? So it's easy to create large-scale lattices, not like 4 by 4 by 4, but more like 40 by 40 by 40 or more. Right? So, okay, so this kind of system would then somehow mimic the properties of the kind of system that you want to study or that you want to simulate, and therefore would be very much tailored to this specialized task of simulating quantum systems. Okay, so here is what we want from such a system. And now it's getting a bit tougher, because there are various things that you need to do a good computation. Quantum mechanics is all over the place, but you really want to have very special things. Well, the first requirement is that you don't lose the superpositions very fast. Physicists would say you need long coherence times, which means that the qubit degrees of freedoms that you want to work with have to be well isolated. Right? They shouldn't interact with everything else and thereby destroy their superposition coefficients too fast. That's one thing that you need. The other thing is, you need to have interactions that you control very well and that are strong enough that you can get the system to do what you want. And here's already the basic inherent problem, because these are conflicting issues. Right? If you want a qubit that is very well isolated, it is also difficult to touch it and to make it turn the way you want. So for example, nuclear spins in a molecule are extremely good qubits. You have very, very long coherence times, but by the same token, it's not so easy to tell a single nuclear spin what to do or to read it out. Right? So, and there are more things like that. So you have to be able to measure them efficiently, right? That would be the readout signal. If you want to be fast compared to the coherence times. You want to, what else? Sure, there should be low intrinsic noise on the system. Then it's important that you have scalability is the issue, that you can build up. It's fine if you can make a few quantum switches, so to speak, but you want to make a large computer, so they have to interact in a good way, and that's called scalability. One thing that should not be underestimated is that you need to be able to reset the system, or to make an initial preparation which is very clean, so that you actually know what kind of state you're working with. Again, that requires strong interaction and is to some extent in conflict with the other things that you want. So even though quantum systems are all over the place, situations where you have a combination of these things are not so frequent. But still there are various, so what I mentioned would still be systems which are seriously studied experimentally, where people try to implement this sort of thing. So here's an example of an algorithm that also I want to use to illustrate also a little other point. So ion traps are systems in which so here's a configuration of electrodes. That's a typical cartoon that you see in a talk. So the 4 electrodes, and you see a little string of greenish ions sitting there in the middle that are trapped there by these electric and magnetic fields. Here is the real thing. It's actually a bit older. It's not the latest model. Just to give you an idea of the size, that would be 1 centimeter there. And somewhere in this between these electrodes, you have sitting a string of ions. Here there are, 7 ions. And you could see them by exciting them with a laser and looking at the fluorescence light. Then you see them like that under a microscope with a CCD camera. That's the way they usually take these pictures. So the qubits would be you select of each ion, you select two internal states, and the distinction between these two is what you call your qubit. Then you can manipulate them singly by focusing lasers with suitable frequencies and pulse shapes and pulse durations also. So you can change the states of the individual ions, and they have an interaction via the vibrational mode in this trap. So if one of them absorbs a photon, sort of also gets a kick, and it will be kicking the others. And that's the kind of interaction that you use. So this is what's called the phonon bus, so the way these systems can interchange information. So here is a version of the Doge algorithm that was run on this in 2003 in Reinhard's group in Innsbruck. So you have to build this coherent coin. Actually, the way to do that is to allow, this has to be a reversible operation, and therefore here's the function f that you're encoding. And this is the way, so here the different values of this coin. This is actually similar to the possible 1-bit gates that I used before. And there are different ways of implementing these with lasers and operations that they can do in this lab. And so two of these would be fair and two would be fake coins in this language, right? So they build a sequence of steps in this of computation that would simulate one of these 4 coins, right? And so here is the Doge algorithm, which is actually extremely simple. What you do is you make an entangling operation here. They know how to do this. This is supposed to be this figure 8 sling. And the 2 qubits are actually the internal excitation of the atom and the motional degree of freedom. Those are the 2 degrees of freedom that you use here to run this algorithm. And so here is a picture of the algorithm. So there are four different coins that I put in. So here the longest time is taken for the implementation of this coin operation. Here are pulse lengths, and the colors code the frequencies that are used. And so you get 4 different evolutions, but in the case of fake coins, at the end you get 0 outputs, and in the case of fair you get 1 outputs. Right? So this whole thing, you see that the whole thing works. It's a straightforward implementation of the Doge algorithm, but where the difficult part is actually building the coin, a coherent coin. Now, these points are done the following way. You start the experiment, you run you run up to this time, and make a measurement. That gives you a 1 or a 0. Right? Then you do it 100 times or so, and then you get a frequency with which this happens, and this will be the position of this dot on this axis. So for each one of these points, they had to run the entire experiment, let's say 100 times. I don't know the numbers now, how much they actually took, but something of that order, right? So for each point here, they're running it 100 times. This is not the way you would use the algorithm. What you would do is you would run the whole thing, just look once at the end, and you see here that you get a very good discrimination between fair and fake. So all these points here are following, it's just the red lines are the theoretical curves, what they should see according to the design of the algorithm. And all these dots are really superfluous. They're only there to monitor to see that the algorithm is really performing as planned. So you interrupt the computation at all these times, make statistical measurements of where you are or what you were getting, and those are these points. So this emphasizes that these are statistical, quantum mechanics is a statistical device, and you can follow it like that. Okay, so so here's actually the experiment, right? Nobody ever said that a quantum computer would have to be small. Right? Well, here it is. Let us compare this with ENIAC, right? And see what we can expect. So on the time scale here, we have 60 years that it took from ENIAC to things that you would seriously call a supercomputer today. So these are 60 years. And So let's say what we really should be thinking about is what happens in another 60 years. Right? So what could evolve from this sort of thing in the next 60 years? That's the question we really have to look at. Maybe not 60, but well, you name the time scale. Right? But it certainly took a long time from the first switching arrays to something that you could seriously call a computer, and from there to something that you could call a supercomputer. And quantum computing is really at the early stages. So when are we going to see a quantum computer? So one of the things that has to be mentioned here is that if you look at Moore's law, then there's something always a bit naive about such extrapolations, because one of the things that you can just estimate is if you come to this range here of numbers of transistors per chip, you're getting down to atomic dimensions. So there is no way that traditional chip design will help you to do this. You need quantum mechanics to, if only to control the errors that you will be making, because if you ignore quantum mechanics, you will just make mistakes. If you ignore quantum mechanics at the atomic scale, you'll be making mistakes. So in some sense, quantum computers are bound to become, computers are bound to seriously deal with quantum mechanics not too long from now. And the field of quantum computing in some sense is sort of a preview of that, but a positive one, namely trying to utilize the effects that you will see at this scale rather than only treating them as errors. Okay, so this is one answer. So we are going to see it sometime there around that time. So the more answers. Well, the quantum PC, right, would be a quantum computer that you buy in a computer shop and put on a table or buy for your own personal use, personal computers. Well, in all likelihood, we are not going to see this ever, because the problems at which quantum computers are really good are very specialized problems, right? And I can tell you that word processing is not among them, right? So the typical things that you want to do with a personal computer, on those, the quantum speed up will most likely not give you any advantage. And these things will be expensive for some years to come. Right? So it's very unlikely that for the PC kind of computer, you will ever see quantum being implemented. Now, for the quantum simulators, that's different, right? So these are problems that people are trying to do on classical computers. They're trying very hard. Some of the real supercomputers of our time are busy with that kind of problem, right? Simulating large lattice systems, quantum lattice systems. And there, the situation is really different, because there are proposals out there and money being spent on the concrete project of building simulators of that type in optical lattices, for example. Well, they're not quite there, certainly, and it will take some time probably, but not a very long time. So these are really existing ideas, existing technologies that might take you there, right? I'm fairly confident that we're going to see something interesting. So what I would like to see certainly would be solving some simulation task that people would have liked to do on a classical computer but failed because of this dimension blow-up. Right? So the next thing that we can ask about is the quantum Shor-class supercomputer. That's the universal quantum computer, something like that would run any possible quantum computation and do so efficiently. Now, that's the real issue here, and the complicated one. Charlie Bennett had a nice answer. He's one of the fathers of this field. So around 1989, I heard a talk from him when he said, well, maybe we'll see it in the next millennium. So very, very nice way of giving a non-committal answer. There have been polls about this. So, for example, in 2003, so people, well, actually, this was asking people in the field, and most of them said, well, maybe on this time scale of 30 years, you would find something like that. But I should also not say that there are some skeptics who say it won't ever happen, right? So this issue is really open. I was certainly not giving you some of the hard problems in quantum computation, which is error correction and do things like that. That will be really tough, and it's not really clear whether the whole thing, whether in the end you will be factoring numbers with these devices. I think it's to some extent an open problem. So my own answer to this is that the important thing here is the aim of this field. It has been the starting point or the focus of a new research field. And whether or not we'll see a Shor-class supercomputer in the next 50 years or not, we'll learn a hell of a lot by trying. And what it certainly will turn up is certain new ways of coherent handling of quantum systems, and being able to manipulate small systems has always turned up interesting applications. They may not be the quantum computer in the end, or the Shor-type quantum computer, but it's bound to be interesting, fascinating, and most likely also useful. Right? So I guess finishing with the timeline, we're somewhere from the range here of first applications of quantum information theory that are really technically there, especially in Singapore. We don't really know about the quantum supercomputer. Somewhere on the line here, there's probably going to be the quantum simulator in the form of some kind of cellular automaton. I'm fairly confident about this, but there's a long way to go here. So I guess the next generation of what you're going to call a supercomputer is not quantum, probably. Okay, so thank you for your attention, and sorry for going over time.
Thank you, Reinhard, for really a fascinating lecture. Louis Chen, the director of the Institute for Mathematical Sciences, has a little token of appreciation for you, after which we will entertain some questions and maybe even have answers.
Yes, I'll try. Sure.
So thank you very much for your wonderful lecture.
Thank you very much.
All right? Okay. Okay, thank you.
Okay.
So who is going to ask the first question?
So you use the light bulb experiment to illustrate the difference between mathematical impossibility and physical feasibility. And then you say it's impossible to have, to translate quantum information into classical information, and the basis for saying that is a mathematical proof.
Yes. Well, based in the framework of quantum mechanics, of course. So if quantum systems are well described by quantum mechanics, actually that was my definition, right? Then I'm entitled to using these natural laws that people have come up with for quantum mechanics in 1926, use them and to do this computation and prove that it's impossible. Actually, this impossibility is related to a number of other things, and you can have a simpler proof that even doesn't use quantum mechanics if you know that if you assume that you have a violation of Bell inequalities, and if you assume that you do not have causality violations in the form of sort of instantaneous signaling between these two devices, that's enough to prove that you cannot have this kind of translation. So it's not just a property of quantum mechanics. It's certainly true in quantum mechanics, but any theory that doesn't have non-local signaling and is able to describe Bell inequality violations will have this feature that you cannot translate to classical and back. Is that an answer? Are you saying it's just a mathematical theorem? Maybe. Well, ask a mathematician what they think about something being just a theorem. It's the strongest kind of statement that we can make. And of course we have to base it on the known natural laws. If somebody believes that, well, maybe there should be superluminal signaling, well, I can't stop them. But there's no evidence at all for this kind of thing. So I think we are on pretty safe ground saying that. Certainly it's a feature of quantum mechanics as we know it.
Other questions?
Hans?
Well, about this quantum simulator, that really deserve the term quantum computer, or is it analogous?
Is it just an analog computer? Right? Yeah, that's what some people say. Now, I don't think that this is a distinction one should get very hot about. Because in the end, what counts is that there is a problem that you want to solve, some simulation problem. You want to study the dynamics of what happens, I don't know, in a large spin system when you are excited in one place and how spins align and things like that, right? So this is the kind of thing that you would study, would like to study. If you can do this by using another system that shows you this, that's fine. I mean, you get the answer. The one thing that one has to say here is that this is not the same as running the system that you really wanted to study in the first place. So people are making models, and you would like to understand, does this model explain what you're interested in? So it's not an answer to take a magnet and say, oh, the magnet is a magnet, and therefore somehow the simulation works, because this way you will not have understood anything. So you want to be able to tune the constants in your model in such a way that you understand the mechanisms. And for that you need something where you can sort of freely program the interaction strengths between the various atoms, and this is a possibility you have in these simulators, which you cannot readily do in for the real system. So for the real system, what people do is they squeeze, right? They put several tons of weight on a little crystal, and thereby shrinking the lattice constants a little bit, and thereby changing the interaction. So this is the kind of tuning that you can do on real systems, but it doesn't tell you whether your model really has the explanatory power that you designed for it, and therefore you want a computer that does it. And that kind of condition would be satisfied by this kind of simulator. Sure. That's well, as I said, I mean, it's a yeah. It's not to be looked down upon anyway, and whether in which department this should be funded is a question that doesn't really worry me too much.
Any more questions? I think we have exhausted the audience.
Sorry about that.
So let's thank the speaker again for a wonderful lecture.